at age of 10, he received a gift for his birthday. The gift was a book called Natural Wonders Every Child Should Know. It is a book explaining several wonders of nature in a language understandable for kids. The book told about how the brain basically worked, how embryos grew, and that plants had some kind of organization in how they developed into an actual plant. It is laced with beautiful images. And the boy's name? Alan Turing. In typical Turing style, as we saw before, in order to bring down the number of possible codes to check, he developed a part of the theory of Bayesian statistics just on the go. And, well, due to the secrecy of all those codes and hush-hush, he didn't publish this theory. And today, in big data, that's the buzzword of today, big data, Bayesian statistics are an important tool of analysis. Treating it like an unorganized machine, that AlphaGo Zero, they only gave it the rules of the game Go, basic rules, and they let it play against his daddy, AlphaGo. So AlphaGo Zero was trained by AlphaGo. And within 40 days of learning, AlphaGo Zero was capable of beating AlphaGo. So AlphaGo beat the world champion, and AlphaGo Zero beat AlphaGo.
I come from a science fiction writing background, so I find Alan Turing a very, very bright and inspiring person because he was such a visionary. So I just want to go straight to the nucleus of him as a person. What actually defines Turing as a genius? Because he was capable of these incredible leaps of coming to the conclusion of a concept without going through like the orderly way as it was perceived back in his days.
Well, I think we have to realize he was really a loner, and I think this helped him greatly. And the other thing is that apart from being interested in mathematics, he had a deep interest in the natural world. And as Peter already explained, what was very important was this book, Natural Wonders Every Child Should Know. And in a time when there was a very clear division between applied mathematics and pure mathematics, Turing didn't take this distinction. He was interested in both. And I think he was, in this sense, the right person in the right time who was able to combine logic with the concept of a machine. Because in 1936, for mathematicians, it was crazy to think of a machine doing mathematics. And Turing was already thinking, okay, this machine cannot only do calculations, it can basically do every kind of information processing that we now have in our computers. The computers, they take information from sound, from images, video, everything. And in a way, you can tell that he already foresaw this. The Turing machine is, well, actually, if you take your smartphone or a laptop, they are all exotic embodiments of the universal Turing machine from 1936. And I think if Turing would have lived long enough, I think he would have seen that the computer basically comes from the development of logic and mathematics. And the human brain comes from millions and millions and millions of years of biological evolution. And that leads to the fact that the human brain is very good in, for example, pattern recognition, which for a computer is very hard. Actually, in 1956, the founders of the field of artificial intelligence, they thought, what is very difficult for a computer? Well, chess is really very hard. What is very easy for the computer? Well, you know, just seeing and interpreting what you see, that must be very easy. So we give this as a 3-month project to some students. Well, and now we are in 2017, and this problem of interpreting what a computer sees is still not solved. Whereas, as Peter already told, in 1997, Deep Blue beat Garry Kasparov. So I think if Turing would have lived long enough, he might have seen that we shouldn't always compare the computer to the human brain. And
in this period, just after the war, the idea of universal principles as a basis for our society has been very important and very inspiring to those who set the foundation. That really is the start of the era that now we live in. I think we are now coming to a time where we're really starting to look again at whether or not that principle of universality can still guide us today. But we can see that the advances bring some parts of the world, well, to new stages that are almost unthinkable, and other parts of the world that are completely disconnected, but which doesn't leave them without an agency, without a wish to be part of this world. And so that kind of fragmentation is resulting from a universal approach that is underlying the logic that we have. And I think that is really very fascinating. And I think what you were saying in your opening words is that in a way that is what Alan Turing embodies, because he has this very logical mind, but then his own life doesn't fit with that world that he's part of. And I think that is just really fascinating.
He talks somewhere about teaching a machine to do things, but he didn't realize that the way you teach the machine is very much culturally dependent. I mean, it's in Japan different than in the Netherlands. So, and of course, you can be a very bad teacher to artificial intelligence, and then it can do very bad things. And like you say, I agree. Yeah, he didn't realize so much of the social context.
He did complain about von Neumann having a very American solution towards like constructing a computer. I think that was like one of their arguments.
Okay.
Because it was like too much engineering and not enough mathematics. What is the state of dealing with the appearance of artificial intelligence in society? Like, how are we dealing with these new concepts? What are the challenges for us as a society with dealing with these entities and also the power they come with, their corporate power, but also their social power?
Well, I think that one of the big challenges where we are at is, I mean, you were asking the question of error, but then we have to understand what error is. And so we can understand an advance in artificial intelligence as long as we have clearly defined ideas of what that will bring in terms of advance. But at the same time, what we are seeing is that we are more and more in kind of social islands in which we understand our own world and we get the information that feeds into our own world, but we have no idea of what is outside of that. So as much as we have an ability to use machines to know, it also creates our own limitations on that understanding. And I think our biggest error is that we don't know that.
Our brains have two functions in reproducing and staying alive in order to reproduce. So maybe there's some kind of immortality argument for a species, which is very ending in a Darwinistic perspective. But as ideas are concerned, I like to think of the idea of computability, or for that matter, uncomputability, is immortal in the sense that we keep learning it and keep learning it.
But don't you agree on the fact that computing is physical? It's something done by a machine built of atoms.
Yes, yes.
So it's not something in the air.
No, and that's my problem with current computers. So, as I said, Watson and AlphaGo are basically Turing machines on steroids, but basically they're not Turing machines because they lack proper infinity. A Turing machine, what Benny already said, was it reads something, it reads the contents of one part of a tape, and based on what he reads, he goes to the left or to the right and writes a certain value. That essence of writing and making a decision is the essence of a Turing machine, but it hinges on the part that it's got an infinite tape, which is physically impossible. So basically, if you want to have a physical universal Turing machine, you need an infinite memory. You have finite states, you have a finite amount of states, but it's got an infinite tape, an infinite amount of memory, which it can reproduce or can work on.
Turing, being logical as he was, would know that infinite cannot be expressed as a number. You know, infinite is not a number, so you cannot know what it is. And in the same way, immortality is the opposite of life. Numbers we can know, and infinite we don't know. Life is concrete or physical, is here, and immortality we don't know. So I think that he would approach that in that same logical way, which means that you cannot reduce infinity or immortality to something that can be expressed in knowable units.
I find it a kind of mystery that the human brain, which is something which is limited, finite, which is made of matter, consumes energy, can come up with the concept of infinity and deal with it in mathematics. I find it a wonder of science. But I do think that, as I said before, that computing is something physical. It needs matter, it needs energy, and all these things are finite. So we can dream about immortality, but I think from the physics point of view, it's an impossibility.
So we can think of infinity from a finite point of view.
Oh yes, but a circle is very much finite. I can draw a circle in a finite amount of space, and still I can draw that circle for an infinite time, and it's still finite. It's what Hegel calls a good kind of finite, infinite, and there's the drudgery of the wrong kind of infinite, where you keep repeating and it's the same all over again, and it's +1 every time. So that's basically Cantor's kind of infinity. And I would like to add to your observation that the human brain is capable of capturing that concept of infinity. I specifically remember and feel the lecture I got from my logic teacher, where he introduced the concept of ordinal logic. Ordinal logic is reasoning beyond the finite, and beyond the infinite. So you embrace the first kind of infiniteness, and you start counting again from that point onward, and you get a whole new world of new kinds of infinity. And what I actually learned there was that there are several kinds of infinity. Actually, there are infinite kinds of infinity.